In our last section here in Chapter 10, we're going to begin talking about vectors. Vectors play an important role in physics, for instance. That's where I'm used to seeing them. But let's get started. So a vector is a line segment, but this line segment has a length, but it also is very important for the direction. This is what you'll see a lot with forces in physics. So it's going to have an initial side and a terminal side, which is just what it sounds like, where it's starting and where it's ending. And another important part is going to be finding what's called a position vector. So all vectors are not started at the origin, but it'll be helpful for us to often find that position vector. So let's get started here. The first question is, let's find a position vector. What they're telling us is that we have an initial part of this vector and a terminal part. Let me see, I want to graph it here. So here's our initial point for this vector, and here's where it ends. So you see it obviously has some length, and it has a direction to it as well. Now we'll talk more about those features of a vector in a little bit, but let's start by saying, what would this vector be like if it had been moved right to the origin? Now it's really pretty simple to do this. What we're going to do here is we're going to do the terminal value of x minus the initial, and then we're going to do the terminal of y minus the initial. So what we're finding is, what is the length of the x component of this vector, and then what's the length of the y component of this vector. That's all we need to do, because if we're starting at 0, we would go that distance in the x and we would go that distance in the y. So that's all we're doing. We're taking the x part of the terminal point, subtracting away from the initial. And then obviously the x component, we've traveled 4 in the x direction. Now let's do the same thing here for the y. The terminal is 4 minus 3 for the initial. And so obviously we've also gone 1 in the y. So this one's pretty straightforward and easy to see. So we're going to give this is our position vector, 4, 1. Notice it's not a parenthesis. I don't know what the technical name of these would be, but we've got these braces or whatever they would be to designate that this is a vector. So 4, 1, so if we start at the initial, we're traveling 4 in the x, 1 in the y, and we've replicated that vector that we had originally found going between 2, 3, and 6, 4. Okay, so same thing here, but this time what's happening, let me jump right to the picture. This time the math works itself out, but notice we're starting in quadrant 2 and we're going to quadrant 1. So we have to account for the distance here, needs to account for the fact that we started with a negative value of x. But the formula does that. So if my terminal is 4 and I'm subtracting away negative 3 for my initial, so my terminal part of x, my initial part of x, do you see that's 7? And that's how far we traveled in the x direction. So the formula takes care of this. There's really nothing to worry about. I'm just trying to show you what happens here. So we do it the same in the y. Terminal is 5, initial is 2. We get 7 and 3. So this vector, 7, 3, would be if we started from the initial, we've got our position vector, we're going 7 in the x, 3 in the y. It gives us everything we need for that vector. Okay, this is kind of silly here. I'm not sure what this has to do with anything. Okay, so this is just drawing one here. So we have this vector starting at the origin and terminating at the point 3, 5. All right, now the magnitude is the length of this line. And if you think about it in terms of the position vector, this is all stuff we've seen many times before. If you start at the origin here, all we need to do is create a triangle. And the magnitude is going to be the value of the hypotenuse here. And then if we needed to find the angle, which we will in some instances, we've done this as well before, it's going to be the y component over the x. We're going to do the tangent. So the tangent of theta would be the y over the x. And all we'd have to do is the inverse tangent. We've done this several times at this point. Okay, so let's play along here. So first we're going to find the position vector. We know we start here and we end at -2, -5. So let's find the position vector. So our ending x minus our starting. Our ending y minus our starting, and we gets us this. So here's our position vector. Now, let's find the magnitude. The magnitude is nothing more than the hypotenuse. It's the same exact formula. We're always going to take it as absolute value. We're going to make it positive. We're not going to take, so remember, you square root, it's plus or minus. We're just going to take the positive value because it's a length. So we've got 6 square root of 2 here. Now, how about the direction? All we're going to need to do is do the tangent of theta. So we're going to put, if my position vector is here, 6, negative 6, tangent of theta is y over x. So I'm just going to make it negative 6 divided by 6. We're looking for what angle creates a tangent of negative 1. Well, if you did this on your calculator, you're going to get negative 45 degrees, or negative pi over 4. So we know this before, but now we don't want a negative angle here. So we know that this point, 6, negative 6, is in quadrant 4. So instead of negative 45, I'm just going to spin all the way around and make it 360. Or we could have done it in radians, but I'll just leave it as. So we could spin all the way around so we get a positive angle of 315. Okay, let's show that two vectors are equal to each other. Now, you could do this by checking their magnitudes and their angles. That would prove it as well. And I'll show you that, but it's much easier to just make them, start them both at the origin. So if we check their position vectors and we get the same position vector, they're the same vector. So we did our terminal minus our initial for both the x and the y, we get this. We do our terminal minus the initial, and we get the same position vector. So these are the same vectors. They're the same thing. Now, you could have done it again by just checking the magnitudes, and then you could have done their angles, and you get the same angle for both of them. Now, just want to point out one more time here, what were our initial? Well, yeah, so the if you inverse tangent this, you got negative 39.8. And the reason that is because inverse tangent is going to give you values in the first and the fourth. So remember, if you wanted to make this a positive value, you'd get the same value for a tangent. The period is 180, so you could have just added 180 to get that. That's a side note. Just remember that the issues that we would have with inverse sine and inverse tangent that we've seen before. But so the point here is the easiest way to do this, to see if these two vectors are the same, is simply find their position vectors. If those position vectors are identical, then the two vectors are identical. Okay, there's a good introduction. We're going to continue this. I think we've got 2 more sections on vectors coming up.